In the last video, we took a look at uniform circular motion in a horizontal plane. And I'd like to pick up here by taking a look at some special considerations when the circular motion is in the vertical plane. So we'll start by thinking about riding some sort of loop-de-loop type roller coaster. So as the roller coaster is going over the loop-de-loop here, okay, they're trying to raise their hands here. There we go. So as they're going around the roller coaster in the loop-de-loop, we have to think about what forces are acting on them. And let's look specifically at the very top. So at the very top, we can go ahead and draw a free body diagram for our roller coaster here. Let's start by doing force identification as always. So I draw a circle around it. It cuts through the track. I'm going to ignore static friction here, just because any static friction is happening in the horizontal plane, and I'm mostly focused on the vertical plane here. There is a normal force. Then we go and look at long-range forces. The usual suspect shows up, gravity. So if we just look at the vertical part of the free body diagram, what are we going to have? We're going to have gravity pointing down, and we also have the normal force pointing down. Because remember, the normal force has to point perpendicular to the surface that exerts it, and as the roller coaster would like to move by Newton's first law in a straight line. That would be crashing into the bottom of the loop-de-loop here. And so the track will be pushing down to keep the roller coaster train car from flying through the track. So the normal force also points down. And it can't point up, although more on that in a bit. So for a normal roller coaster in normal operation, both gravity and the normal force points down. So we can figure out how fast the roller coaster is going by applying Newton's second law of motion here. So since everything is down, and at the very tippy top, we would be this would be the one spot where we're not having a change in speed. So at this instant, no change in speed. So the acceleration will be pointed straight down in towards the center of the curve. Coming up here, where the roller coaster is slowing down, it's going to be pointed, it wants to point into the center, but it's also slowing down, so there'll be a piece acting against it. So the acceleration will actually point a little bit off center over there. But over here, the acceleration points straight down when we're at the top. So this is screaming for us to just choose down to be positive, because literally everything's pointing down here. So let's just do that. So we go and look at the y component of motion here. And we have that our net force is going to be the force of gravity, because it's acting entirely in the plus y, plus the normal force, again, acting entirely in the plus y. And that has to equal ma. Now here, because we're moving around in a circle, and there is no horizontal component to the acceleration right at this spot, we can note that the acceleration would have to be equal to v squared over r. The force of gravity is mg, and we have to leave the n there. All right, so we can go ahead and solve for the speed. So if we divide through by m, we're going to get v squared over r equals g plus n over m. Then we will multiply through by r and take the square root. So v will equal the square root of r times g plus n over m. All right, so here's the deal. This tells us, at least in this case for a roller coaster, that there is a slowest speed that the roller coaster must, that there's a minimum speed the roller coaster must be going at the top of the loop-de-loop if it's going to stay on the track. And what do I mean by that? Well, if the normal force can't go less than 0, because it can only push down, it can't pull up. And so the smallest value this can possibly be is 0. So when the normal force is 0, we get a critical speed, and that's what this gets called. Of the square root of, rg. Now notice I said critical, not minimum. More on that in a minute. But at least in this example, you can't go slower than this and still stay on the track. If you tried, let's say if you're coming in at lower than the critical speed, if in order to be here, you would need v to be less than v critical, what the actual path is going to be is it'll follow the circle here, and then it's going to fall off in a parabola until it hopefully reconnects with the loop-de-loop. Okay. Now, designers of roller coasters have thought about this. And so if you look at the trucks on the roller coaster car, so this is the bottom of the roller coaster car, and there's the truck. You'll usually see that they've got attached onto it, I'm not going to draw this very well. There's going to be two very large wheels that look kind of like that. And then if you look, there's usually a very small wheel like that. And the idea is that it passes through the track like this. And so in normal operation, I should probably have my track pointing the other way for the example. There we go. So in normal operation, the big wheels are interacting with the track, and you get the normal force pointing perpendicular to the track. This is if we were, say, at the bottom of the hill, the way I have this drawn right now. In fact, actually, let me flip this. There we go. That's better. So at the top of the loop-de-loop, our normal force is going to look like this. And if for some reason you're going at less than V critical, so here, if V were less than V critical, what would happen is you would hang on this emergency wheel right here as you're going along. And this emergency wheel would interact with the track so as to provide an upward pointing normal force. That way you could effectively get, because we said down is positive, that way you can get a negative normal force. And this is done just in case something horrible happens that they have to hit the emergency brake on the roller coaster or something like that, and it doesn't have enough speed to get around the top of the loop-de-loop. These emergency wheels will do the trick. Okay. But in normal operation, the normal force can't go negative. And so this critical speed would be the minimum speed you need to be at the top of the loop-de-loop. Now, this can cut the other way. If you've ever driven over a hill at speed, you'll discover that this critical speed can become a maximum. So let's say you're driving your car at the top here. So now here, let's go ahead and do this. Again, I'm neglecting static friction and drag and stuff like that at the moment. I'm just going to focus on the vertical part of this. There's a normal force, and we identify our long-range forces. There is a force of gravity. Again, we'll draw a vertical free body diagram. And so here, we'll still have gravity down, but now that this is a car going over a hill, you'll have a normal force up. And notice that I made this shorter. So again, since we're going around the curve like so, at the very tippy top, we need the acceleration to point down. So once again, I will make down positive. So we can repeat exactly the same analysis we did before. We go take the y component of Newton's second law. Now it's going to be the force of gravity minus the normal force equals ma. So mg minus n equals mv squared over r, because again, you're going around in a circle, and this would be the radius of the hill here. So again, we can figure out our minimum speed, and it's our speed that we have, and it's just what we had before. We're going to get that v is equal to the square root of r times, now it's going to be g minus n over m. And again, it's the same deal. The normal force can't, if the magnitude of the normal force would go negative, that means it'd be pointing down. The normal force can never point down when you're driving your car over a hill. It can only ever point up. So again, at minimum, the normal force is 0. And so when the normal force is as small as it can possibly be, that again is our critical speed, root rg. But now the difference is this is our maximum value. So when we were doing the roller coaster loop-de-loop before, this was our minimum value. And here, this is our maximum value. So this does give us a way to think about circular orbits. So for a circular orbit, remember we've said that, say this is my planet, and I'm putting a satellite in orbit around the planet. All right, so if this is my satellite orbiting the planet, the whole trick, remember, is that it is going sideways exactly fast enough that it falls around the Earth. So again, it's the same deal. It'll always be accelerating in. We can do a force identification diagram for this. So let's do it. Oh, hey, whoops, sorry. Didn't mean to make it that big. Oh, hey, the circle cuts through nothing. There are no contact forces. Our only force is the long-range force of gravity. So We can go ahead and draw a free body diagram. Gravity, that's it, literally. Since that's literally the only force, the acceleration have to be pointing down right up there. We knew that already. And so again, this is screaming for us to say down is positive at this exact moment. All right, so we can do the same drill. In the y direction, we can say that the force of gravity has to be equal to ma. So we get that mg equals mv squared over r. Oh, hey, it doesn't matter how massive your satellite is at all. We get that the orbital speed is, you guessed it, our critical speed, root rg. Now note, if this were the Earth, g would be less than 9.8 newtons per kilogram here because we're away from the center of the Earth. That's something we'll get into a bit in the next video. But suffice to say, at the height of the International Space Station, it's a lower number than 9.8. But whatever g is at the altitude you're at, that's the speed you need to go to make a circular orbit around a planet. And it kind of makes some sense, because if you think about it, this is the limiting case between our loop-de-loop roller coaster and our car going over a hill. With our roller coaster, the normal force had to point into the center of motion. Here, it had to point out. So here, the speed had to be at least root rg. Here, it had to be at most root rg, or else you're going to go flying off the hill. So here, where there is no normal force, it has to be where those two conditions meet. At least root rg and at most root rg meet at root rg. Alrighty, so in the next video we will introduce the Newton's law of universal gravitation and figure out how you can weigh a planet. Catch you in the next one.